we've talked a lot about acids and bases, but now I mentioned water, and water has the ability to be what's called amphoteric, which means it has the ability to be an acid or a base, depending upon the situation and what's next to it, what it's interacting with. I want to talk about something else, though, associated with water, and it's called autoionization of water. If you think about it, it'll make sense as to what this means. If you had to pick two ions that water was made of, what two ions would you pick? Okay, hydrogen and, I said ions, not just elements. What ions would make up water? Hydrogen is one. What are you left with? What does a hydrogen ion look like? What's the charge? Okay, so you got H plus 1. What do you got left in a water molecule? And another hydrogen. What ion does that make? Hydroxide. Good. So if you have a hydrogen and a hydroxide together, you have a water molecule. So when I'm talking about autoionization, what you have is water molecules that actually autoionize themselves. In other words, they can separate out and form hydrogen and hydroxide ions in solution. Okay? Now this happens only just a tiny, tiny bit. If this, a solution of water, or I guess just even if it was pure, liquid water is technically, from a chemical perspective, a very, very, very weak, extremely dilute solution of hydrogen ions and hydroxide ions, because most of the molecules you're looking at are actually bound together as H2O molecules. However, every once in a while, a very, very extremely small amount of them are autoionized, and they separate out into ions. And then they usually join right back and form molecules again, and it's just over and over, okay? And there's just a few of them at any given time that are autoionized. So water can be an extremely weak, pure water can be an extremely weak electrolyte, but it is a very bad electrolyte. The only reason that it has any electrolytic properties at all is because some of those water molecules actually have ionized at any given time. All right, so about 1 out of every 10 million water molecules are going to go through this process known as autoionization at any given instant in a sample of water. Okay? And there's what I mean by autoionization. Now, it is reversible. That means when they form, they can easily just reform back into what they were. Another way to look at this is, because what actually happens is you don't get, this thing doesn't just fall apart, okay? Because water, we know, is not held together by an ionic bond. Water is held together by covalent bonds. So as easy as it is to want to look at this and see how there is a hydrogen and a hydroxide that could come together to make this, which is what happens when you mix an acid and a base together, but realize that since this is not an ionic compound, what technically happens is you get two water molecules next to each other. And when two water molecules come next to each other, one of them acts like an acid, one of them acts like a base. One of them will pick up a hydrogen from this one, like this one, will grab this hydrogen and make a hydronium ion, which is the same thing as having a hydrogen ion, because it's just a water with an extra hydrogen. And the other one will be stripped of its hydrogen, left with a hydroxide ion. So this is what it seems to be chemically, but what actually is happening is what's written in the second equation down here. Okay? So that means that all aqueous solutions, anything that's dissolved in water, will always have at least a tiny bit of hydrogen and hydroxide ions in that solution, right? If you take a sodium chloride solution, excuse me, and drop it in, solid sodium chloride, tiny little pinch, dissolve it in water, you've got a sodium chloride solution. What all ions are present? Well, sodium ions, chloride ions, and water molecules. Also, though, because 1 in every 10 million water molecules react with themselves, you're also going to have hydrogen and hydroxide ions floating around inside this water. But it's going to be very, very small, very weak, to the point where we don't even measure it. We just neglect it most of the time. But if we were to look at something, there's a number here that's very important. If we were to take a sample of pure water, and we can measure it, and it was at 25 degrees Celsius, about 1 atm, what we're feeling about right now, if we looked at it, we would find that in a pure sample of water, since they react 1 to 1, for every free-floating hydrogen, or hydronium ion, there tends to be a free-floating, one equivalent free-floating hydroxide ion. So it's sort of a one-to-one dissociation. What we're saying and what we've monitored to be true is that the concentration of the hydrogens present is equal to, obviously, then the concentrations of any of these hydroxides present. That's assuming you don't have another solution. Like if you have a sodium hydroxide solution, this is not true, right? Because there's a whole lot more hydroxide ions in there now. I'm talking about just pure water. In a sample of pure water, this concentration is equal to this concentration of the stuff floating around. And that actually has a numerical value that remains constant. It's 1 times 10 to the minus 7 molar. 1 times 10 to the minus 7 moles per liter. So that means in a sample of pure water, on average, if you had to calculate the concentration of hydrogen ions floating around in pure water, it would be 1 times 10 to the minus 7 moles per liter. So very, very small. Likewise, hydroxide would be exactly equivalent to that in pure water because they come from each other. They come from the same process. So whatever process produced this had to be the same process that produced that. So they should be one-to-one. All right. Now, why is this important? Well, let me ask you a question. You've heard of the pH scale before, right, from like other science classes or just life in general. What do you know about the pH scale? How high does it go? What number does it max out at? 14. What is considered the middle, the neutral point? See that? 1 times 10 to the minus 7. I'll explain these exponents in a minute, but they're all going to be related to the pH scale. I'll show you why. Okay, so this brings us to what's called the ion product constant of water. It's a fancy way of being able to multiply, going back one slide, these two concentrations together. If this is 1 times 10 to the minus 7, and this is 1 times 10 to the minus 7, what's the product of that? You multiply those two together, what do you get? 1 times 10 to the what? Minus 14, right? 1 times 10 to the minus 14. How high does the pH scale go? 14. Okay, so the ion product of water is just that. Taken in a perfect sample like that, if you multiply the concentrations together, you're going to get a certain product. But we're going to take that a step farther and say that in pure water, each one is 1 times 10 to the minus 7. Hydrogen, hydroxide. Multiply it together, you get 1 times 10 to the minus 14. And what we're going to say even further is that 1 times 10 to the minus 14 never changes. That is always the ion product constant for water. Now, if your hydroxide levels increase, that means your hydrogen levels decrease, so that whenever they're multiplied together, you still get 1 times 10 to the minus 14. Okay? That's what we call KW. It stands for the ion product constant of water, and it will always be 1 times 10 to the minus 14. Okay? Now, in a pure sample, it's going to be split evenly. Half of it's going to be 1 times 10 to the minus 7. The other half is going to be 1 times 10 to the minus 7. Hydrogen and hydroxide. In an acid sample, guess which one of those concentrations are going to be higher? Hydrogen or hydroxide? Hydrogen. Okay, so you'll see that the 1 times 10 to the minus 7 will get to be a bigger number, right? When you have a minus 7, how does your exponent change when the number gets bigger? Does the actual number, 7, go to a lower number or a higher number whenever you are in that situation? For example, let me rephrase the question. Let me ask it a different way. Which number is bigger, 1 times 10 to the minus 7 or 1 times 10 to the minus 6? Which one's bigger number? Minus 6 is a bigger number, right? The pH scale. The lower the number, is it more acidic or more basic? Remember? The lower the number on the pH scale, like down to 3, 2, 1, that's very acidic, right? Because of these exponents. Okay? The lower the actual value, what the pH scale represents are those exponents taking away the negative sign. Okay? So if you take away the negative sign, it makes sense that the 6 is greater than the 7, right? And the 5 is greater than the 6. Okay? That's the way the pH scale works, and that's why it seems to work backward. I'll show you more here in a second.